This is a paper submitted to the A2I conference, entitled Enhancing Signature Verification with Siamese Neural Networks, a pre-trained backbone approach. Signature verification is crucial in biometric authentication, distinguishing genuine from forged signatures. Traditional methods struggle with variability in genuine signatures and detecting skilled forgeries. This research employs Siamese neural networks with pre-trained convolutional backbones to learn robust signature representation and improve verification accuracy across different styles and forgery techniques. All approaches include traditional CNNs. Earlier CNN-based signature verification systems treated the task as a classification problem, training models to distinguish genuine from forged signatures. Though CNNs learn spatial features well, this approach needs many samples per user and struggles to generalize to unseen users. Siamese neural networks compare signature pairs using twin CNNs with shared weights. They learn to distinguish genuine from forged signatures by minimizing distance for authentic pairs and maximizing it for fakes. This enables verification of unseen users with limited data. Neural networks are a class of machine learning models inspired by the human brain. They consist of interconnected layers of neurons, where each neuron processes inputs, applies a weight, and passes the result through a nonlinear activation function, like ReLU or sigmoid. These networks are typically organized into three types of layers. Neural networks learn by adjusting their weights and biases through a process called backpropagation. Using a method known as gradient descent, the goal is to minimize the loss function, which measures how far the predictions are from the true values. Input layer receives raw data, example pixel values, from an image. The hidden layers perform computations and extract hierarchical features. Deep networks have many such layers, hence the term deep learning. The output layer produces the final result, such as a class label or similarity score. For image tasks like signature verification, convolutional neural networks are commonly used. They capture spatial patterns using convolutional filters. CNNs are neural networks specialized for image data. Unlike traditional networks, they utilize the spatial structures in images. The core CNN component is the convolutional layer, which applies slide-in filters, kernels, to detect local patterns like edges and textures. These filters create feature maps that capture key visual features. CNNs typically include convolutional layers, extract local features. Activation functions like ReLU introduce nonlinearity. Pull-in layers downsample the feature maps to reduce dimensionality and focus on the most important information. Fully connected layers combine features for classification or other tasks. Siamese neural networks compare input pairs by measuring their similarity. They employ twin subnetworks, typically CNNs, with shared weights, where each processes one input. The resulting feature embeddings are then compared using distance metrics like Euclidean or cosine distance. During training, the SNNs learn to minimize the distance between embeddings of similar pairs. Example, two genuine signatures, and maximize the distance for dissimilar pairs, a genuine and a forged signature. This makes SNNs particularly well suited for verification tasks, even when there's limited data per class or user. Pre-trained models are neural networks that have already been trained on large datasets, like ImageNet, to learn general features such as edges, textures, and shapes. These models capture rich, transferable knowledge useful for many visual tasks. Transfer learning is the technique of reusing these pre-trained models for different, often smaller tasks. Instead of training a model from scratch, we fine-tune a pre-trained model or use it to extract features from a new dataset. This saves time, requires less data, and often improves performance, especially in domains like signature verification where labeled data is limited. To enhance feature extraction and improve generalization, several Siamese networks were built using popular pre-trained CNN backbones. For example, the VGG16 is pre-trained on ImageNet, making it effective for transfer learning, and it performs well in tasks with limited datasets. ResNet18 benefits from residual connections which help prevent vanishing gradients, allowing the network to learn deeper and more stable features. EfficientNet B0's smaller size and lower computational cost make it suitable for faster inference or deployment on devices with limited resources. DenseNet121's dense connections help reduce redundancy and enhance feature propagation, making it especially good at learning subtle differences useful in tasks like signature verification. MobileNet V2 is optimized for mobile and edge devices where computational resources and memory are limited. In deep learning, particularly in computer vision, a backbone refers to the main architecture or feature extractor of a model that is responsible for learning and extracting high-level features from input data, such as images. It is typically a pre-trained convolutional neural network, CNN, or another model like ResNet, VGG, or EfficientNet that serves as the foundation for more complex tasks. The original model is a 27 million Siamese neural network without a pre-trained backbone. The size of the models with pre-trained backbones are as follows. The Siamese neural network with VGG16 backbone is 55% of the original size. The ResNet18 based backbone is 42% of the original size. EfficientNet B0 based backbone is 17.45% of the original size, and DenseNet121's backbone based approach is 27.62% of the original size. However, MobileNet V2 backbone is only 10% of the original size. In this study, two widely used datasets were employed to train and evaluate the Siamese neural networks for signature verification. These datasets provide a rich variety of genuine and forged signature samples, helping to enhance the model's ability to distinguish between authentic and fraudulent signatures. SIDAR dataset contains 2,640 Latin script signatures from 55 users, offering both genuine and forged signature samples collected under controlled conditions. The diversity of the signatures helped the model learn fine-grained handwriting details, which improves verification accuracy. The ICDAR 2011 SICOMP dataset consists of 1,585 Latin script signatures from 64 users. This dataset was used for evaluation to test the model's generalization capabilities. Evaluating on a different dataset helps reduce overfitting and provide a more realistic measure of the model's performance as signature patterns vary across datasets. To preserve essential signature features while standardizing inputs for deep learning models, the structured preprocessing pipeline was applied. The process started with converting RGB images to grayscale, simplifying computation while retaining essential structural details needed to differentiate authentic and forged signatures. All images were then resized to 224 by 224 pixels for uniformity. Since pre-trained CNS backbones typically expect RGB input, the grayscale images were replicated across three channels, ensuring compatibility without losing structural integrity. The preprocessing pipeline standardizes variations from different devices while enhancing writer-specific characteristics. It strengthens meaningful spatial patterns and reduces noise, creating a uniform input space that improves the Siamese network's embedding comparison. In the Siamese network, embedding generation transforms raw signature features into compact and meaningful feature vectors that reflect the writer's unique style. The feature extracted by the backbone are distilled into a 1D vector using global average Boolean, which summarizes spatial patterns while ensuring robustness to shifts and rotation. A projection head, typically a fully connected layer, then reduces the dimensionality of these features, producing embeddings that emphasize discriminative, writer-specific characteristics and suppress irrelevant noise, for example, the scanner artifacts. To structure the embedding space meaningfully, the network is trained using triplet loss. It minimizes the distance between genuine signature pairs and maximizes the distance from forced ones. This results in an embedding space where Euclidean distance corresponds directly to signature authenticity, enabling threshold-based verification. The architecture of our models are outlined in the figures shown. The first figure is the baseline Siamese network architecture, and the second figure is the architecture for the Siamese network with the pre-trained backbone. The receiver operating characteristic ROC curve is a tool used to evaluate the performance of binary classifiers. It plots the true positive rate against the false positive rate at various threshold settings. This helps visualize how well the model distinguishes between genuine and forged signatures across all decision boundaries. The results of our models are shown in the figures above. The figure on the right is for the original Siamese model, and the figure on the left is of the models with the pre-trained backbone. The area under the curve summarizes overall model performance. Higher AUC means better class separation. To select the optimal threshold, the point closest to the top left corner, ideal classifier, is chosen, often using Newton's J statistic. Confidence interval around the AUC provides insight into the model's reliability and stability. Our test results are shown below in the bar chart. The results worth mentioning are that the VGG16 is by far the best performer, with more than 15% improved accuracy over the original Siamese model. We can notice that all of the models behaved in a similar kind of way, although most of them have very different architectures and very varying sizes of parameters. A model worth mentioning is MobileNet V2, which is only 6% lower overall accuracy than the original Siamese model, despite being only 10% of the size of the latter. Thank you.